Hello everyone, welcome to the tutorial using SPSS to conduct PCA analysis, okay? So on your canvas, you should have at least two files. One is called PCA tutorial, the other would be the PCA data, okay? Let me show you my screen, okay? Okay, hope everyone can see my screen here, okay? So first, we will have a Word document called PCA tutorial. You can see it here. Not so sure. Yeah. Okay. You can see it here. Okay, PCA tutorial, and it records each steps in details, how to conduct principal component analysis. So the data we use in this tutorial is from Professor James C. Dennis, who unfortunately passed away, I believe, 2 years ago. But he, very generously shared this example to the internet so everyone can have access to this data. And this data is for a teaching evaluation. And I revised its data to have a simplified format so that we can use it and have some better understanding of principal component analysis. And just to let you know, this illustration is only to show you how can we conduct PCA and how can we read the result from SPSS. Once you learn these techniques, you can apply these skills into the data in public affairs. So this data is not really from public affairs, just a teaching evaluation. So let's see. So first, we recall that in the regression model, we have this linear format, and because we have too many independent variables, the n is super large. We try to reduce the dimension from n into I, a smaller number of independent variables, and we assume there exist several principal components can be written in a format of the combinations of each independent variable in the original regression model. And after lots of transformation, we get a simplified regression model with y corresponding to several principal components. And since I is smaller than n, we reduce the dimension. Okay, how can we conduct in SPSS? So let's first open SPS. Okay, after you open SPSS, you should have a window like this. You may also have a pop-up window. You just close that pop-up window, it should be fine. If you are using Windows instead of Mac like I am using right now, you may have different interface, but the button, the order of those functions should be the same, or at least similar. So once you have this window, we need to load the data. As we mentioned before, the data is about teaching evaluation, and I put the data also actually Dr. Yento Chandra helped me to put those data into the canvas. So you can see it here. We'll use this teaching evaluation as our PCA data, and we'll use the other one SAQ as our factor analysis data. So for me, I store it in this data folder, and for you need to download it from Canvas and into any location on your personal computer. So how can we load this? We go to SPSS, open file, excuse me, open, not imported data, okay? Open data and find this file teaching evaluation PCA.sav. This SAV file is SPSS recognizable data file. You don't need to import. If you're using other format of the data, for example, Excel data or CSV data, you have to use import data to choose corresponding entry to import the data in different format. So here we just directly use open. Let me do it again. Okay, file, open, and data, and get this teaching evaluation. Okay, and click open. After a while, the data, is loaded into SPSS. There are two views. Here is data view and variable view. Okay, so you can see me using an iPad. So that's why I'm looking down a little bit. We can see for the variable view is a description of all the variables. We have this faculty, sex, faculty, ethnicity, nationality, and student sex, student race. And we can see the value of them. 1 represents male, 2 represents female. Excuse me. You can see the measure or types of those variables, whether it's nominal, it's ordinal, or scale. So scale in SPSS means continuous numeric interval, all those mathematical and calculable data structure. So, but actually when we go to the data view, we see those are still, the Likert scale from 1 through 5. So see 5, 4, 5, 4. I believe those 5 should be satisfied, but I'm not so sure because I don't have the metadata, which is the data to describe the data. And unfortunately, I haven't found it on the internet. So I would guess 5 would be, extremely satisfied. But if not, don't blame on me. So we have to, find the metadata to understand the real meaning of those numbers. Okay, so even though it's Likert scale from 1 through 5, it's still treated as a scale, as a continuous variable. That's why we can do principal component analysis here. Okay, so it's the step. We load our data, and you can find our data through this web link. And now our data is shown here, and also give you a overview, an overview of every data set in this data set, the meaning of each variable in this data set. Our interest is to reduce the dimension from the item 13 to item 24, which are the satisfaction score for different questions. So we try to reduce this, probably 1, 2, 3, 4, 12 variables, 1, 2, 3, 4, 11, yeah, 11, no, 12 variables into some number of principal components. Okay, after we load the data, we try to do PCA. So in SPSS, let's go back to SPSS. In SPSS, sorry, I need to move the Zoom thing back. Okay, it's kind of not annoying because it's block my view. Okay, how can we conduct PCA? We go to analyze, dimension reduction, and factor. So you can see, as I told you, PCA is quite similar with factor, and they are doing similar thing here. So dimension reduction, factor, okay? We'll have a pop-up window. So you see the pop-up window, the title is factor analysis, just ignore it. You can try to do a PCA. Now we try to select all the variables of our interest and move it into the variable window. So it should be instruct through the end. So all the 12 variables into variables, okay? Then we go to descriptives. Okay. In descriptives, we see lots of function. We check coefficients, we check reproduce, we check KMO, Barrett's test, and we will interpret all those results later once we got the result, okay? And hit continue. That's the setting for descriptives. Second, we go to extractions. In, you see, okay, why can't I hit extract? Yeah, hit it. So in restriction, we can see the method here, principal component, right? there are several other different methods we can introduce later. So we choose principal component. Now we're doing PCA. And here we see based on eigenvalue, here set into 1. Because when eigenvalue is less than 1, the correlation between the principal and the independent variable could be ignored, is quite low. And we also try to check this security plot. It's very useful, and keep everything else as default. So it's 25 iteration, and it will definitely converge. So we don't need to worry about the iteration, and continue. And we go to the third one, rotation. Okay, so click the rotation, which will give us a new window. Like I said, without any rotation, we may see several different principal components, but it is quite difficult for us to understand the meaning of those principal components. A rotation will help us to see the different view of the components, and we can have a better explanation of that. So what is a rotation? It's not quite easy to explain it through the video, but we can have some discuss in class. So now we just remember we need to do a rotation so that we can have a better explanation of those principal components. Okay, so for orthogonal rotation, so that means each principal component should be perpendicular with each other. That means the correlation between each component should be 0. So the typical method to do such rotation is called Berry max. So try to maximize the distance between each principal component. And we also check with loadings. As we mentioned in the previous video, loadings are the coefficients to show the relationship between principal components and the independent variables. So we also keep everything else default, so we don't need to worry about the convergence right now. And let's go to the fourth option, score. So here we just check save as variables and make it regression, keep everything as default, and continue. And option will be last one we need to do. We see missing value, exclude cases like listwise or exclude cases pairwise. We just list cases listwise, which means so if we can't deal with those missing values, we can probably delete the whole I believe should be the column. Okay, if not, correct me. Okay, then we need to check those two boxes behind. So one is sorted by size, the other is suppress all coefficients. Here we see the meaning of suppress all small coefficients. So when the coefficient between the principal component and the variable is quite small, we ask the computer not showing them. It doesn't mean their correlations are 0. It just doesn't show it. So here currently the threshold is 0.01, which means if the correlation coefficient is less than 0.1, it won't be shown on the result in SPSS. So we try to change it to 0.3 because we think 0.2 correlation is still quite weak. So everything less than 0.3 should not be shown. So let's change it to 0.3 and close. Why 0.3? Like I said, it's just still a rule of thumb. You feel that those correlations are quite small and negligible. Okay. After we setting off everything, we just click OK. And the SPSS will help us to run the principal component analysis, the PCA, and here's the results. Okay. The first result is correlations. So those are the correlations between each independent variable, the original variables, not the principals. So we can see it is diagonal matrix. We have the 1 for each one because it's correlation to itself, right? We can see the first one in structure scholarly graph. It has the 0.66 correlation with structure well prepared. So it's a strong correlation, not very strong, but still a strong positive correlation. We can see several things like that, right? So here we go to this KMO and Bullet test. So KMO will tell us the sufficiency of sample size, okay? Like we mentioned before, if the sample size is too small, we cannot, test we cannot conduct a statistical test in a meaningful way. Like we learned in the previous weeks, a rule of thumb of sample size should be 30. It means if you want to find the statistical significance, at least you need to have 30 observations. Here, if the KMO score is greater than 0.6, then the sample size should be fine. Now the KMO score is 0.9, so it's way fine. So sample size is sufficient for our PCA. And the other thing is called Bullet's test. So what is this Bullet's test? Bullet's test is a test with null hypothesis that the correlation matrix is identical matrix, the identity matrix. So what is an identity matrix? Identity matrix is everything on the diagonal, is 1, and everything else is 0. What does that mean? It means every variable is independent with each other. As we discussed before, if every independent variable is independent with each other, so true independent variable, okay, then we cannot do PCA because you cannot reduce anything, right? It should be a square matrix, and you can't do anything with that. So here, the significance is 0. We reject this hypothesis, which means the correlation matrix is not identity matrix, right? Okay. The third result is called communalities, which reflects the percentage of variance explained by the factors. So here we can see, we still don't know how many principal components yet, but we can see the 73% of this variable is explained by the total components. The second one, second variable, extract scholarly graphs is, the 69% of the variance explained by those components, and so on. Excuse me. So here is the total variance explained. So here is not the percentage of variance of each individual variable explained by the factors. It's actually the percentage of variance, total variance of the equation model explained by the factors. So let's see, the first component explain 52% of the variance of the total model of the response, okay? The second component is 10.25% of total variance. So in this example, the SPSS only give us 2 principal components, and here we can see a cumulative percentage. So the 2 principal components account for 62.32% of the total variance. So it explains the response quite well, more than 50%. So now remember the square plot, right? We see the computer give us 2 principal components, but why 2, right? How many principal components we can have? Actually, we can set the number of components before we when we are doing the analysis. But there are some criteria to select the maximum, the optimal number of components. The script plot is one of them. So the vertical line is above the eigenvalue. The horizontal line is the number of components. So the number of components is 1, the eigenvalue is more than 6, which is good because we mean eigenvalue is greater than 1, which means has the correlation between the variance and the components is significant. It's quite strong, right? So until a point, the eigenvalue is less than 1, which means the components doesn't provide a better relationship with the correspondence. So here we can see 1 component equals 2. the eigenvalue is still greater than 1. But if the component goes to 3, it should be less than 1 because, it's 0, it's 2, and the half should be 1. So if it's 3, the eigenvalue is less than 1, and it's problematic. So based on scratch plot, the number of components should be 2, which is the optimal size. Okay, so that's the usage of scratch plot. And here's a component matrix. Like I said before, those things are called loadings. Okay, so we have component 1, component 2. So that's PC1, PC2. And what are this 0.89, 0.819 mean? It means the correlationship between this variable and the first component is 0.819. So this is also the coefficients. So this means PC1 equals to 0.819 times this variable plus 0.806 times this variable. Notice that those variables are illustrated as the label of the variable. Still remember here? Let me show you. Okay. So remember in the original data set, we have the data view and variable view, right? So everything in this end result, we only use the label of the variable, not the variable, the name of the variable. Okay. So name of variable is like item 13 or something like, but the label here, label column is the instructor scholarly graph. It's not in the alphabetical order, so just be noted. We have to find the corresponding variable name. Okay, so here, since it shows as the label, just use the label to see. So it should be this coefficient times this coefficient times this, sum them together to construct principal component 1. Similarly, we have this to construct principal component 2. So based on those linear relationship, it is quite difficult to understand what is PC1, what is PC2, right? It seems like they consist of everything. So for example, in PC1, only 3 are omitted here, and for PC2, only 4 are omitted here, right? And we also know we have a threshold of 0.03. So those are omitted here does not mean they have a zero correlationship. They might have, but just less than 0.3. So we just ignore them. So it's difficult to, I'm sorry. Here, okay, I'm sorry. This is PC1, this is PC2, okay. PC1 have lots of, everything, okay. PC2 have something. But after rotation, okay, we still have some problematic, we still have, this part of things that's commonly shared between PC1 and PC2, but it tries its best to get this, rotation. So PC1 is something like instructor prepared well, or whether the scholarly grasp, whether it's confidence, whether focus on lecture is something like instructor. I don't know, probably something like subjective, proactive action. And PC2 is like instructor allows me to ask question. I'm satisfied with student performance evaluation. Instructor accessible to student outside class. It sounds like PC2 is something about communication or interaction between the teacher, the instructor, and the students. So first is about the preparation of the instructor. So how the instructor prepared the class, the lecture. Second is like how the instructor interacted with the students. So it's much easier to explain than the unrotated one, because in the unrotated matrix, PC1 is related to everything, right? It's everything. If it's everything, you can tell anything, right? Okay, sorry for that. And here's the plot for the rotation, just for an illustration purpose. Okay. So after that, let's go back to our tutorial. So after we conduct all those PCA analysis, we'll have a final result. Okay, so RC represents rotated. So PC is non-rotated. So pre-rotated components. RC is rotated components. So finally, we'll get this kind of form. Here I use I37, I13, I13, I14, but it might be wrong because I use the alphabetical order, but the label is not listed in alphabetical order. So you need to check with the variable view which label corresponds to which variable. Okay, just be noticed about that. Okay, that will be it for principal component analysis.